there is. Okay, yeah, and the last part is just a few pictures, so don't get discouraged by the page number. It's going to progress slowly, but we'll get there, don't worry. So what is a filament packing? So I depicted 5 different kind of cylinder packing. So I'm going to use the terms cylinder, filament, and rod packing interchangeably. For me, they're the same thing. And so I depicted 5 different kinds of filament packings. And you can see that some of them are straight and some of them are helical. And this already maybe aids to understand that I don't really assume that the cylinders are straight. They can curve around each other. They are infinite in one direction in my assumption, and they are 3 periodic. So they're periodic in each of the 3 space dimensions. And in the top, we have, oops, that was a laser pointer, never mind. In the top, we have 5 unit cells, and in the bottom, we have like copies of the unit cells, right? And I'll be particularly interested in this talk in 2 kinds of these rod packings, namely the pi plus and the sigma plus rod packing, because they have very nice geometric properties that we're going to discover later on. In particular, I can already see that they're quite helical. And maybe another thing that I should say is I'm not interested in the static behavior of these rod packings, but rather in the quasi-static behavior. This means that I want to extend the rod packing in one direction and see how it behaves, right? I'm not interested in only one state. I'm interested in an entire deformation. So again, I'm interested in these 2 rod packings that are depicted on the gyroid minimal surface. So for enumerative purposes, all of these 5 rod packings, or actually rod packings in general, can be plotted as line arrangements on bicontinuous minimal surfaces. So these are the primitive surface, the diamond surface, and the gyroid surface. And the curvy structure of this gyroid somehow enables this helicity of the pi plus and the sigma plus rod packing that we can also see here, right? They're the most helical, the most curved arrangements out of all of these. So yeah, how do we model these? The classical thing to do is to use tensegrities, and maybe some of you now are going to scream at me why I chose to do this definition, but bear with me for a second. So for me, a tensegrity framework is an embedded graph that consists of vertices of edges that are subdivided into cables and bars, not into struts. I don't use struts at the moment. But so this is why maybe it's a bit controversial, but for me, I only want the contractive forces of the cables, and I'm not interested in the repulsive forces of the struts. And the bars are modeled by Euclidean distance constraints, and the cables are modeled by one-sided Hookean springs. So they just want to contract, and this gives me a nonlinear optimization problem. So I think of this in terms of optimization, basically. On the left, we have the 3 prism, and it is a rigid framework, I believe, with 3 bars and 9 cables. And curiously, I mean, mostly you are aware of it, I guess, but curiously, this is a structure that stands on its own, even though the bars are not connected, right? And this is kind of intriguing to me still. But anyway, mostly you're aware of this, I guess. And we call a framework diperiodic, or in our setting, 3 periodic, like I said, if we can, if we basically have a unit cell that we can copy throughout space to, like, I don't remember the name, like to cover the entire space. So we have a periodicity group that is represented in the translational space of RD, and we have a compatible action with the placement of the tensegrity framework over there. And that's very natural, right? Deperiodicity means we can just copy a unit cell and get the entire framework back. And now, like I said, I don't want to look at these frameworks in a static way. I don't want to look at their rigidity, but rather I want to expand them, contract them, and deform them, basically. So I need the concept of a deformation path. And this is a curve in configuration space that respects the bar length equations and maintains the periodicity. This doesn't mean that the periodicity needs to stay the exact same way. It can change a bit, but this means that we don't get an additional unit cell suddenly on top of the first one or something like that. It just stays maintained. And this finally enables me to give maybe the most important definition of my talk, which is the definition of geometric auxeticity by Bossier and Strainu, that they've worked a lot on. And so if we take the lattice at time tau2 to time tau1, this gives us a unique linear operator T. And if this unique linear operator is a contraction for all times that are in some interval, right, then we call the deformation path auxetic. So the intuition for this is if you have a material, for example, imagine a sponge, and you expand the sponge in x direction, then you would expect that the sponge shrinks in the lateral directions, right? But curiously, these Tensegrity frameworks, what they do is they expand in the lateral directions. And maybe this already motivates why auxeticity is something that engineers and chemists are looking into, because there's an immediate application to this. When you contract a framework and it contracts in the lateral directions too, well, then it becomes very easy to store it. It takes up a little, like not a lot of volume, right? And in the other direction, if you expand it and expand it and it expands in the other direction too, then you get a very porous material that doesn't weigh a lot, right? And some of these auxetic materials are, when you click them into one of their configurations, like when you fix them at some point, because they're flexible, right? We're doing flexible deformations. So when you fix them, they're quite robust. So this is in particular why aerospace engineers are looking into these things, for example. Right. So one very standard example of auxeticity is the inverted honeycomb framework. So the unit cell is actually 3 edge orbits and 1 vertex orbit. So you can recognize it here. And we stretch it in x direction for from an extension of tau x to 0.6 in the unit cell up to 1.25. And in the first 3 pictures, we recognize auxetic behavior. So we expand in x direction, and we see that the y direction also expands up until this maximally extended rectangular configuration, the bottom left. And from then on, if we keep extending, then the y direction shrinks again. So it's not auxetic anymore. So this is an example where we have both auxeticity in the first 3 pictures, and then after that, a non-auxetic path. But like I said, this geometric auxeticity is kind of a new concept. So mathematicians have only started looking into this quite recently. But this topic has been at the interest of physicists and engineers for quite some time, and they used a different definition of auxeticity. And I'll try to relate these 2 concepts in a bit. So what they use is the so-called instantaneous Poisson's ratio. And we consider this ratio Ex, and it's a ratio in the lattice extension. So Lx is the lattice extension of the unit cell at time tj. And we subtract from that the lattice extension in x direction at time tj minus 1, right? And we divide by some normalizing factor. So this term, if we expand in forward time, this is positive, right? And then again, if we have Ey and it expands in forward time, then this term is also positive. So the Poisson's ratio, which is depicted on the left, mu xy, this term will be minus 1 times a quotient of 2 positive numbers. So it will be negative. And this is how we define auxeticity in the engineering sense. And I guess one may wonder why the Poisson's ratio is with a minus sign before it, right? And my interpretation is that this is an unnatural behavior. This is something that is not expected, so they gave it a negative number, I guess. And the expected behavior would get positive numbers here. Anyway, in a recent study, we were able to relate these two concepts, but with quite a caveat that I'll tell you about. So if we have a deformation path that is auxetic, we get a non-positive Poisson's ratio for free. We don't get negative because auxeticity is smaller or equal to. But in the other direction, for this theorem, we have to assume that the lattice has an orthogonal representation throughout the path. And this, of course, is a strong assumption. And if we have this orthogonal unit cell, and the Poisson's ratio is positive, non-positive for all discretizations, so again, this is a strong assumption, right? Then the path is auxetic. So how do we show that if we measure a material, like engineers would, if we measure a material, how would we show it for all discretizations of this unit interval? Well, we have to assume something more. And I think if we assume something like Lipschitz continuity or smoothness, then a very tiny discretization should at least give a good insight. But this orthogonal unit cell and for all discretizations, these are strong assumptions, and this I want to hammer home. We have a slight generalization of this theorem, which is very technical, but for this reason, I didn't show it. Surprisingly, a lot of the configurations that we see in these rod packings are actually have an orthogonal unit cell. So maybe this assumption, so almost numerically orthogonal unit cell, let's say. So maybe this assumption isn't so far off. Anyway, so finally, I'm in a position where I can talk about the Tensegrity model for pi plus. So this has been published 2 years ago, so it's quite recent work. And so we consider the rod packing on the left, this curvy linear cylinder packing. And along the central axes of the cylinders, we place cables, right? And whenever two cylinders meet, we place a bar. This is because we want the cylinders to stay 2r, 2 radius apart at every point. I mean, this is a quite natural assumption. And I forgot mentioning something in the beginning. These configurations that I showed, so maybe let me get back real quick. These configurations are actually rope length critical, meaning that if you were to contract them or expand them in any direction, they would increase their length, so the rope length, the central axis length of these cylinders. And this I exploit here by when putting the cables at the central axes, they want to contract as much as possible so that this rope length criticality is again achieved. Basically, this is the idea. So we end up with the picture on the right. These are two filaments in tight contact. And we place cables along the central axes and a bar in the center. So now you can imagine, is this rigid at all? Well, no. If you have these cylinders, they can just pass through each other. Like this Tensegrity could just flip. And this is a problem, right? We don't want it to flip. And for that reason, they in their paper, they deduced some balancing conditions from the configuration space of two filaments in tight contact, which is actually quite well understood by mathematicians. And with these balancing conditions, they were then able to formulate a model that actually behaved well. So this is then their model, and in equilibration, it behaved well. So when they only wanted to find one configuration, this is a good model. But then they tried to deform it and try to apply stresses to it. And you can see here on the right-hand side, I depicted the lattice extension in y and z direction. And in the bottom, we have the Poisson's ratio that I just mentioned. And you can see that in the beginning, we have quite a chaotic behavior of this. I mean, this is not expected. We have a very symmetric framework, and we want to just continuously deform it, but we have a chaotic behavior. So this is something that we don't want to see. And in addition, we have on the left these two like the Tensegrity models that we deform, and after the first few steps, these chaotic steps, we have a break in symmetry. So the nice and symmetric model on the left isn't represented anymore after a few steps. Also, we have, so I didn't mention this, but we have 3 extension cycles and 3 compression cycles. And they did that because in the chaotic behavior in the beginning, they didn't want to see anymore, so they wanted to have to relax and compress and expand again to get something meaningful. And so finally, another thing that is undesirable is, but maybe this is a bit of a pet peeve, but these 2 curves are not equivalent. But this framework is so symmetric that you would expect that they would be, right? There's not really a difference between the y and the z direction. So this again is not really what you would want to see. But however, they were able to show that this particular model of Tensegrity framework was actually auxetic, because the Poisson's ratio is clearly negative. So this particular model showed auxeticity, which is nice. But we wanted to make this model more robust. We wanted to fix these problems in our recent work. And so we tried to look at the configuration space of 2 filaments in tight contact, because we thought that this is the thing that kept the model from being as robust as we'd like it to be. So 2 filaments in tight contact, like I said, if they are orthogonal, are mathematically well understood. If they are incompressible and wrap around each other, then the mathematical theory dictates that there's a contact line between the 2 filaments. And if you let them compress a little and be a bit elastic, you find that there's actually a whole surface of contacts. And in a recent study where they did finite element simulations and X-ray tomography, they found that these 2 filaments actually have varying pressure on this surface. So there are 4 distinguished points where the pressure is maximized. And if you have 4 points in space that are not collinear, you can connect them by K4 and get a tetrahedron, right? And the tetrahedron has nice rigidity properties, as probably you're well aware. And so we wanted to exploit them. And so on the left, we have, again, the model that was proposed before. And this is our new model on the right. Replace the contact bar by an entire tetrahedron. I'm not going to go into details. It's all available online, but it's just boring formulas. So we again want to have that the bars are 2 radius apart. So this is the blue bar, the cylinders. This is the blue bar, and we add these red cables on the edges of the cylinder. They are supposed to penalize twisting, because this is only for 2 filaments in orthogonal contact. But you can imagine that the filaments could also be in helical contact and so on. But this is not modeled by us right now. And we have these green bars. And this is maybe an experiment that you can all do with me right now. Because when you put your fingers on top of each other and they are straight, then you get a single point of contact. So if they are completely straight, you get a single point of contact. But if you wrap them around each other more and more, then the surface of contact grows and grows, right? And so these bars depend on the opening angle of the orthogonal clasp. So the opening angle of these 2 cables determines the length of these. And then again, we added some balancing conditions that came from the configuration space of 2 filaments in tight contact. And this is our model right there. This again is a nonlinear optimization problem that we can solve with whatever methods we like. Well, we hoped at least, but that's not the case. But I'm not going to go too much into detail for time reasons. But we were able to also, besides this model, we were able to deduce an algorithm that robustly approximates deformation paths but not only numerical approximation, but also with nice theoretical guarantees. So the idea is we get a contact graph. So we basically get the cylinder packing, and we get an extension that we're going to extend it to, right? And we want to output an animation of the deformation path. The first thing we do is replace the bars by tetrahedra, as I told you before. Then we optimize the initial configuration to find a stable equilibrium. This we do by Riemannian optimization. This is joint work with Alex Heaton, so thank him for that. And after that, we apply path tracking, which is a predictor-corrector scheme, to follow the deformation path as we go with an increase in the parameter t. This is a part of the so-called homotopy continuation package, which is numerical algebraic geometry, if you're interested. And this gives us then a way to find the deformation path. And yeah, so like I said in the beginning, we're only at slide 13, but the rest are just basically pictures that I want to show you. So this is the pi plus rod packing that we've seen in the beginning. And I decreased the size of the cylinders so that you can actually see the porosity and actually see what's going on. And so we stretch in x direction for 50%. X direction is perpendicular to the page. And we observe that the y and z direction on the right are increased relative to the initial configuration on the left. All right, this is completely quantitative, I guess. Qualitative, I don't remember. Yeah. And in the Tensegrity model, we see that these tetrahedra, they actually straighten up from the left to the right. And also the cables is maybe not so good. Maybe for the green cables, you see that they straighten up too. And this is what is expected. The cables become straighter and straighter the more you stretch, right? This is what's expected. And now remember the curves that I showed you that were a bit chaotic in the beginning. Now we have two very nice curves, right? They're completely identical even. So we basically fixed the symmetry issue. On the left, we have the lattice extensions, and on the right, we have the Poisson's ratio. And let me just say the Poisson's ratio here is, again, negative. It has a bit different scaling this time, so don't worry about that. We used a different kind of Poisson's ratio to compute this. And again, we have two expansion cycles and two contraction cycles, just to relate it to the previous picture. And with the theorem, we were able to, well, assuming nice assumptions like smoothness, we were able to deduce that this was also a geometrically auxetic path, which is nice. Then we considered another rod packing, which is called the sigma plus rod packing, and this is maybe anecdotally quite an interesting rod packing, even more so than the pi plus rod packing, because we find it in corneocytes. So you find it in your skin, actually, this cell packing. And how can you see it? Well, if you put your hand in water, for example, for a long time in warm water, then your hand wrinkles, right? And this is actually a process that is purely driven by a geometry. Right? So this is a dead process. It's not like your body says skin wrinkle. And how you can imagine it is that these packings of cells, these filaments, they soak up the water and they become straighter and straighter. And by becoming straighter and straighter, they straighten out this packing. And I think they grow by like 100%, but this packing has actually the capability to grow by like 800%. So it's completely magnitudes larger than what the cylinders themselves would be capable of achieving. And again, this is due to the porosity here, right? And again, we see if we stretch in x direction, which is perpendicular to the frame, we find that the y and z direction are expanding too. So we deduce, well, it should be auxetic, right? The Tensegrity model, the tetrahedral model here is not very interesting. I don't know what to say here, but it's also beautiful, I believe. And then we have the two curves. They're again completely identical. So this gives us hope that this is actually more robust and not just coincidentally. And And for the auxeticity, we again find that it's auxetic, as expected, like people predict this. And we verified it. And the same for our theorem. So where does this leave us? Maybe you might have noticed that during my talk, I didn't quite assume that we can slide the filaments over each other. This is the same as saying that the friction of two cylinders is actually infinite. But there's an easy way to fix this. If we, so each cable now has a resting length associated to it, but if we distribute this resting length throughout the entire cylinder, then this is basically saying we can slide the cables to their preferred, or the contact points to their preferred energy point. However, this adds significantly to the already large complexity of this problem. And so we were incapable of implementing this in larger models, and only were able to do it in smaller scale models, unfortunately. Another thing that is a work in progress with one of my collaborators is that we try to apply this model to weavings too. And in particular, we're interested in so-called smart fabrics, which is a very cool concept, because smart fabrics you can basically imagine as a tensegrity model, so an actual tensegrity model, where you can alter the length of the cables parametrically. So you're able to basically, by heating the fabric, you're able to change the resting length, and therefore you can, well, we hope at least that we can get changes in the geometry of the fabric. So we hope that we can get bulging, so changes in the curvature of the surface, if you imagine a fabric like a surface. So this would be kind of cool. We haven't done that yet. And of course, a natural, different natural application would be to apply this to more complex filament packings. And in particular, like I said, we only dealt with orthogonal filament packings contacts up until now. So the helical configuration space, whenever that's understood, and the intermediate spaces between helical and orthogonal, that would be crucial to continue this work. And we've talked to the people that work on this. They say that they solved it. They haven't published it, unfortunately. So we're still waiting. But yeah, that was it for my talk. Thanks for your attention.